Hello, this is the start of session 11 and we continue with chapter 5, which is talking about the structure of polymers. After talking about polymer molecules and the chemistry of polymer molecules, we talk about molecular weight. Usually extremely large molecular weights is observed in polymers with very long chains. By molecular weight, which is denoted by capital M, shown here, we mean mass of a mole of chain. Okay, here not all chains have the same length in a polymer. That is, there is a distribution of molecular weight, so you will see chains with low molecular weight and chains with high molecular weight. Now we want to see how we can calculate the molecular weight based on the distribution of their weight. Here you see distribution of molecular weights for a typical polymer. The first parameter that is defined here is m bar n, which is the number average molecular weight, and it's obtained by dividing the chains into a series of size range and then determining the number fraction of chains within each size range. That's why it's also defined as this term, as you can see, in which MI is the mean or middle molecular weight of size range I. XI is the number fraction of chains in size range I, and WI, which is used in order to define weight average molecular weight. So weight average molecular weight, as you can see, MW. WI is the weight fraction of chains in that specific size range. To understand better what do we mean by number average molecular weight and weight average molecular weight, here is an example, and we want to find these items or this parameter based on the listing of weight of students of a class. As you can see, we have 10 students and we have their mass in pound here. We want to find the average weight of the students in this class based on the number fraction of students in each mass range, and also we want to find it based on the weight fraction of students in each mass range. To find the average weight, we have to list students into different groups with different ranges of weight. To find the number of group, there is or the number of intervals, there is a method, or there is a formula that has been proposed by Bendit and Purcell. It says the number of bins is equal to this number. If the n is equal to 10, so 6 is recommended for this one. But let's assume that we have divided the whole groups into 8 sections or 8 parts, as you can see here. The first group from 81 to 120, as you can see here, we have this one and this students. These two students belong to the first group, so we write down 2, the number of students, the same 2 in the second one, 3, 2, and because in these groups there is no student, we write down 0 in front of them, and finally we add them up. Of course, the total number is gonna be 10. The next step is to find the median or the mean number, the average number of the weight. So if we look at the first group, again we look at the first group, as you can see here, we find the average of these two numbers, which is 110, as you can see here. So on and so forth. So we continue to write down the mean average, or the mean weight or the average weight of each group, and finally we add them, which is equal to this number. This number is equal to the total weight of the 10 students, of all the students. Now the next step is to find the value of xi. Remember that xi is the fraction number. So the fraction number is actually for the number is this one, this term divided by the total. So it's going to be 0.2. And for this one going to be 0.3, so on and so forth. And the weight fraction going to be this one times its number divided by the total one. So is a weighted fraction of this one gonna make the weight fraction. So we will have these two columns added to our calculation. The first one is number fraction, as you can see, 2 divided by 10, 2 divided by 10, 3 divided by 10, so on and so forth. And this one is 2 times 110 divided by total, 2 times 142 divided by total, and then we will have this column. These calculations are also shown here, as you can see. So when we write down the table again, we have number fraction, we have weight fraction, and we have the mean value. So we can easily find the number average from this formula. Xi can be found from this column times its corresponding mean value or mean weight plus the second one, so on and so forth, which gives us 188 pound. And weight average is actually equal to weight fraction from this column times the mean weight, which results in 218 pounds. As you can see, the values found for number average and weight average are different but close to each other. The process to find number average and weight average molecular weight for a polymer chain is also similar. The value of number average molecular weight is used to find another parameter, which is called degree of polymerization, denoted by dp. dp is the average number of repeat units per chain. As chains have different lengths, of course we will have different values, but dp determines the average value. That's why we have to have number average molecular weight and then find it. If we have only a single chain, of course we can count the number of repeat units. For example, in this polyethylene, you see that there is 1 unit here, 2, 3, 4, 5, 6 units. So the average number of repeat units for this chain is 6. To find it for a polymer with different chain sizes, we use this formula in which m bar n is number average molecular weight and m bar is the average molecular weight of repeat units. For copolymers, this is calculated as follows. M bar is equal to Fi, which is chain fraction. This one is actually related to Fi, and Mi, which is molar weight of repeat units. So far we were talking about the polymer molecules that have a linear chain, and we neglected the zigzag arrangement of the backbone atoms. Single chain bonds are capable of rotating and bending in different direction in 3 dimensions, as you can see here in these pictures. If you look at the third atom, the third carbon here, this carbon can stay anywhere in this gray path and still have its angle or its equilibrium angle, which is 109 degree, with the bond between the other two atoms, these two atoms, as you can see here. So based on where this third atom is located, we can have straight and twisted chain segments, as you can see as an example that's shown here in this picture. In other words, chain bending and twisting is possible by rotation of carbon atoms around their chain bond, and there is no need that the chain bond or the bond is broken to have a different or to alter the molecular shape. Therefore, the polymers that consist of large numbers of molecular chains, of course, they can have very complicated shapes due to the numerous random kinks and coils produced by chain bond rotations. The physical shape and physical characteristic of polymer, it depends not only on its molecular weight, but also on its shape and differences in the structure of molecular chains. In other forms, polymer properties depend on items such as molecular configuration, degree of polymerization, and how these chains are related or connected to each other or bonded to each other. Items such as linear polymers, branching, and cross-link, as you can see here. If these polymer chains contain linear chains having some branches, as you can see here, these are called branching polymers. An example is low density polyethylene. Another form of molecular structure is called cross-linking. This is happening when usually it happens in forms of monomers, and they contain strong covalent bonds between various linear polymer, the polymer chain that you can see here, and these bonding between them are a strong covalent bond. Examples are bakelite and melamine, and the picture is schematically shown here. Before we move to the next section, just to remind you that the section talking about molecular configuration, section 5.8, is not part of this course, and will not be in the exam. In case a polymer is made of two different repeat units, this is called copolymers. Depending on how these polymers are synthesized, we may have different form of them. As you can see, random. Assume we have a repeat unit of A, shown in red, repeat unit of B, shown in black. If A and B are randomly positioned, then we have a random copolymer. If A and B alternate in polymer, in the polymer chain we have alternating copolymer. If there's a large blocks of A unit or mer, and then large block of B, so on and so forth, B and A and B, then we have block copolymer. And if we have a chain of B units grafted and inserted onto an A backbone, this is called graft copolymers. Remember, copolymers are against or in front of homopolymer, in which we only have one unit. An example of alternating copolymer is shown here, where we have one unit of styrene and one unit of butadiene, which results in a copolymer called SBr. Crystals can be found as a single crystal. This example shows a polyethylene single crystal. There are also semi-crystalline polymers that consist of a small crystalline region, which is called crystallite. These are having a precise alignment. They are also associated with amorphous regions. The molecular change may look like something like this, and they form a plates. You can see a chain folded structure here for a plate-shaped polymer crystallite in this picture. Here, thin platelets, they have chain folds here at the face, this face, and this face. And generally, it has this chain folded structure. Polymers rarely 100% crystalline. It's difficult for all regions of all chains to become aligned. As you can see, we have some crystalline regions shown here, in this one and this one, that are parallel organized, and in between they have amorphous region. The ratio of these regions to the whole area or the whole regions is showing the degree of crystallinity, expressed as percent crystallinity. Some physical properties actually depend on this crystallinity percent. Heat treating for this type of polymer causes crystalline regions to grow, and of course the percent to increase. Some bulk polymers that are crystallized from a melt are semi-crystalline, and they form a spherulite structure. They have alternating chain folded regions like these ones, and amorphous region like this ones, as you can see here. Spherulite structure is for relatively rapid growth rate. This picture here shows a transmission photomicrograph of a spherulite structure of polyethylene. Here you see a linear border between adjacent spherulite structures. They use cross-polarized light, that's why you can see pattern of black and white here, and of course the black borders clearly here. This is the end of the session. In next chapter, in chapter 6, we start with different form of imperfections in solid. Thank you.